So this section, this whole lesson on 3.5, is what if we have, instead of just one equation, two equations, or three, or four, or five. So we're going to start with just two equations first, but we're going to go through this concept. So let's look at it graphically. If I have two equations, an equation that contains x and y we know is a line. An equation containing only x and y that is linear, meaning x, not x squared, but just x, and just y, not y squared, but just y. Those equations are linear equations. So on a graph, they look like lines, linear lines. As a result, we can have three options. One of our lines could be like this. The second line may intersect it once, right here. One of our lines may be like this. The second line may look like the exact same line and lie right on top of it. The third option is that my line may look like this, and the other line is parallel to it. Do parallel lines ever intersect? No. So, this method here is the graphical approach to what we're going to do algebraically. You are going to watch that video to see how to do this on your calculator, how to find the intersection. The intersection, it's in here somewhere, I think it says it, but I'm going to say it. The intersection is the solution to what we call the system. So that is here. Any ordered pair that satisfies both equations is the solution to the system. And that's where those points are going to intersect each other. So here, where they intersect. This one, there are infinite solutions because they intersect over and over and over. And the last one, they never intersect. So the first graph, let's write this down, has one solution because there's one intersection. And that solution might be like 2, 3. It's a coordinate, right? It's a coordinate. The second option, when the lines are identical, has infinitely many solutions because they intersect infinitely many times. They're literally lying on top of each other, and each point along one of the lines lies on the other line as well. And the third option, they never intersect. So we say, good, no solution. So one solution, infinitely many solutions, no solutions. Very similar to what we did talk about with one variable systems a while back. Let's get right into this concept though. So in the first one, we're going to do two methods to solve. And I know that some of you have seen parts of this. I get it. Trust me, I say it every time. But we're going to go way beyond what you've seen in your regular 7th and 8th grade course. But based on your knowledge, because some of you have that knowledge already, what method would I use to solve a system like this? What method, Alex? Andrew?
Substitution.
Why substitution, Andrew?
Because you have the y equals 2x plus 4, and you can just substitute that in for the 2 times y.
Yes, that goes in for just the y in the 2 times y part. So take what's highlighted in red, and technically I should really just erase the y equals piece there. Hold on. Take what's highlighted in red and substitute it in for what you see in blue. This is substitution principle from chapter 1 this year. Substitution principle. And again, I know that a lot of you have seen this already. Do it. Just appease me. Appease me, please, and do it. So take the second equation and replace y with its equivalent expression, which is 2x plus 4. So take the second equation and replace y with its equivalent expression, which is 2x plus 4. And then solve this equation for x. Am I done?
No.
Why? Who said it? Sean. What are we going to do, Sean?
You need to solve for y by plugging x into the easier equation to solve for formula.
Yeah, good job, Sean. I like what you said. Plug x into the easier equation. Take the shorter root. Don't plug it into equation 2, because then you got to solve for y in equation 2, right? So take this x equals 3, plug it back into equation number 1 at the top. If x is 3, 3 times 2 is 6, 6 plus 4 is 10. This tells me that y equals 10. So how might I write my solution? Write it as a what? Yes, a coordinate point. 3, 10. and this is not to call anybody out, but I just want a quick idea. How many people have seen what we just did before today? And be honest. If you haven't, it's okay. I just want to know. I just honestly want to know. Okay. I'm seeing yes from most. I saw like a half hand from a couple, which is fine. You might have seen it, but you're not sure if you recall it. But you have the idea of it. Substitution method, right at the top. Substitution method. For those that have seen this, they've probably seen the other method as well then. What would the other method be called? Good. A lot of hands. Gus, what do you think? Elimination method. Very good. Elimination method. Some teachers might call it row combination method. It's the same thing. It's the same thing. And later, in your calculator, when you look at the video at home, you're going to learn about what's called a matrix. Honestly, raise your hand if you've heard of a matrix in math, not the movie. Have you actually used matrices in math before? Have you seen it with like, it looks like a box, you have all these numbers in it and stuff? If you have some familiarity, that's good, but I'm telling you now, you probably haven't seen the command you're going to work with tonight, or this weekend.
Is that when you find the line of best fit?
Different one. You can use a matrix for that as well. But this is not. This is finding a solution to a system of equations. Okay? You'll see, you'll watch the video and I'll go through it. It pretty much does elimination for you. The matrix method does the work for elimination for you. As long as you have everything lined up. X, Y, Z, all of your variables have to be lined up. And we'll talk more about that today. So let's get to the next example here. Well, first, let's look at the graphical solution. Here's the graphical solution right there. And what was our answer? Our answer was 310. Notice, people, notice. First, this is in slope-intercept form. So it's really easy to graph, isn't it? Well, there's the intercept at 4. The slope is 2. So I go up 2 over 1. Up 2 over 1. Up 2 over 1. Oh, there it is. Now, the other one, what is this form called again?
Standard form.
Standard form. What might be an easy way to graph something in standard form like we've talked about? By finding the what?
Slope.
You could find the slope of my intercept in standard form, negative a over b, c over d. It works technically. But what might be easier? What might be easier, Nick?
Find the x or y.
Yes, find the x and the y intercept. So the y-intercept in this case, unfortunately, if I set x equal to 0, is 5.5. That's tough to graph. The x-intercept, ooh, that's negative 11 thirds. Also kind of tough to graph. So when your intercept method of graphing a line gives you these funky decimals that are not easy to see, then that might be a case where you want to use slope-intercept and convert this to slope-intercept form, or recognize the slope is just going to be 3 halves, right? Negative a over b is 3 halves, and the y-intercept is c over b, which is negative 11 over negative 2, or 5.5. So I'm at 5.5, and my intercept is 3, and my slope is 3 halves. 3 halves is 1.5. So I'm at 5.5. I go up 1.5 to 7 over 1. Up 1.5 to 8.5 over 1. Up 1.5 to 10 over 1. And there I am. So slope might be a little bit tricky at times, right? Might be a little bit tricky. But recognize that if you use fractions, it makes it a lot easier for you. Avoid decimals if you can. Fractions are nice to use here. Let's look at the second one now. Based on our answers that we just gave, what method might I use for this approach as opposed to the last problem? What do we think for this approach, Clark?
The addition subtraction.
Yeah, let's use that elimination or addition subtraction method. Very good. Now, Clark, can I do it right away? Like right now, could I just add straight down? Is that going to work for me? Is anything going to cancel, Clark, if I add straight down?
No.
No. If I subtract, will it cancel? Unfortunately, it won't either, right? So I need to manipulate, alter, change one of my equations. Which is the easier of the two to manipulate?
The bottom one.
Why the bottom one, I'll tell you?
Because it has the general x, that's just a 1.
Look for the unity meaning 1, coefficient. Look for the unity coefficient or the coefficient of 1. That is very easy to make it into whatever you want. Now remember, with the elimination method, what's the goal? To eliminate. So I need this to become negative 3x is what I need. Now, yes, your teachers might have in the past made it 3x. That's fine, and you subtract down. I like to add straight down, so I always want to have opposite signs. The only way to make this negative 3x is to multiply the whole equation by what number? Negative 3. So let's take, and watch what I'm going to do. I'm doing this, and some of you are going to say, Mr. Howell, this is ridiculous. Why are you doing this? But I'm doing it for a reason. Because right now this is easy, but when it gets tougher, this method I'm showing you will help. Here's what I'm going to do. I'm going to say the following. I'm going to take equation 1. I'm writing a command. It's like a command prompt for computers. I'm taking equation 1, and I'm going to add negative 3 times equation 2 to that. This is my command. I know you don't have to do it. I get it that a lot of you can just multiply the second equation by negative 3 and add straight down. But this will come in handy when we have x, y, and z. If there's 3 variables or 4 variables, it's good to keep track of your steps. So I'm taking equation 1. I'm going to rewrite it. And to that, I'm going to add the second equation times negative 3, which makes this negative 3x minus 15y equals 21. So I'm taking equation 1 and adding equation 2a to it. Why am I calling it 2a? What's the significance of this a after equation 2?
Meaning that you changed it?
Yeah, another version of that equation. And again, I know this is easy because we're doing an easy example. And you're like, I don't need to do this stuff. I get it. Just trust me, please. Take me on faith. I studied engineering beyond grad school. I've done every level of math that's possible in college. You literally will use this later on. I'm telling you now. So the organizational tool I'm teaching you is important. Okay, so add straight down now. Again, we multiplied everything in this equation by negative 3 to give me equation 2a. That's where that comes from. Add straight down. The x's cancel. Those cancel out when I add them straight down. This becomes negative 11y. This becomes 22. Therefore, y equals, everyone?
Negative 11.
Again, Jimmy?
Sorry.
That's all right. Negative 2. I got you. The negative 11 from here. No problem.
Yeah.
So if y is negative 2, which equation would you plug back into here? There's no right or wrong answer, but there's a better answer. There's a better answer. Gus, what's the better answer? Which one? How come?
Because x is isolated and there's no coefficient to it.
Good. It's not isolated, but it has a coefficient of 1. If it were isolated, it would say x equals, right? So the first equation is probably easier because x doesn't have a coefficient. But again, does it matter? No. You can plug it back into equation 1 or back into equation 2 to find out what x is.
So it's like unity, right? Which is x.
Whenever it has a coefficient of 1, we say it has a unity coefficient. So let's go ahead and plug a negative 2 into equation 2. We can see it happening in red there. This is going to give us negative 10 and positive 10 over negative 7 plus 10 gives me positive 3. Agreed? X equals positive 3. So my answer? How do I write my answer? Nick, Trey?
You write it 3, negative.
Yeah. As an ordered pair, please. As an ordered pair, write my answer. What's that?
I thought if you used a certain equation to change it, you couldn't reuse that equation because it would be affected.
So I altered this equation, but remember, this is just a multiple of the original equation. So can I go back from here to there by dividing everything by negative 3? So it's actually the exact same equation as when we started with. So it doesn't matter. You can alter it. You could technically, if you wanted to, you could have plugged into here. Because this is technically a version of that equation. They're equivalent to each other. Right? You absolutely can. Good question. A very good question. Other questions so far on substitution and elimination. Simple problems. X and Y only so far. Okay. Do I show the graph on the next slide? No. Okay. All right. Let's look at these two scenarios. Why don't you work on these by yourself real quick? Work through A and B. See what you get for these two possibilities. See what you get for these two possibilities. Sean, what's up?
I had
Okay, give me a sec. Maybe go on to the next one right now, Sean. Hold on. Ooh. Green one.
I think your battery has to be on.
I was trying to help Jack with his project over there before. He super glued batteries into this container, and he was trying to get them out by like using a scissor, which is not safe. So I said, oh, use pliers, and he couldn't get it. So I used it. I got one out, and when I went to grab the second one, I squeezed the pliers too hard, and the battery just exploded. So that's what's, see all the stuff all over my shirt? That's what's kind of all over me. But like, my eye will not stop itching after it happens, so I don't think it's in there, but it's just hurting a little. All right. The first one, what method did you choose? For part A, what method is what I want to know. Clark?
substitution.
Yeah, I would agree with that. Okay, take this expression, which is equal to y right here, and substitute it in for x. Oh, my pencil just died. Okay, take this expression right here, which is equal to y, and substitute it in there for y. What happens with this problem? What happens here, I'll tell you.
You get no solution.
Why do you get no solution?
Because in the end, the x's cancel each other out, and you're left with an untrue, a false statement.
What is the false statement you end up with? You remember? What does it say?
8 equals 1.
8 equals 1, is that what everybody got? Or like 7 equals 0, something like that, right? But you get a false statement, you get a contradiction. Remember that phrase? You get a contradiction. Why is there no solution to this? Why is there no solution to this? What's happening, Olivia?
They're the same slopes of the
Yeah. They are parallel to each other. They're not on top of each other, they're parallel and they're separate. And if you can't see that, look at the first one. The slope is negative a over b, right? Which means it's negative 1 over 2. Well, the second line, we can see the slope is negative 1 over 2. They're absolutely parallel. What's the y-intercept for the first function, for the first equation? What's the y-intercept for that first equation right there?
1.
Is it 1?
No, it's
1/2. So what we have here is one line. There we go. We have one line that has a y-intercept of 1/2. The other one that has a y-intercept of 4. And they both have a slope of negative 1/2. So therefore, this is what our graph looks like here. Okay, they will never intersect. They will never intersect. Gus?
So I solved it a different way. I'm not sure, like, I was just gonna ask you to accept it. So I isolated y as the first variable.
And then set them equal to each other?
Yeah.
That works too. Yeah, that's a great idea. You ever hear what Gus just said? Let's think about what Gus just said. If you can isolate y in both equations, and if y is y, it means that the transitive property, if me and Gus are the same height, and Gus and Andrew are the same height, all three of us would be the same height. That's the transitive property, what you just did, without realizing it, or maybe you did realize it. So yes, you could solve this for y, and it becomes y equals 1 minus x all over 2. And then you could set this
Yeah.
equal to this right here and solve for x. In this case, x would drop off though again, right?
Yeah.
That works.
It was 0 plus 8 equals
Yeah, exactly. And again, what I want you to recognize is that either way works. Substitution works, elimination works, setting equations equal works by the transitive property. Also substitution, you call it either one. Okay? That works, good job. How about part B? What approach do we take for part B for sure, based on the way it's set up? I would probably not want to use one of the methods here. What method should I use?
elimination.
Yeah, I should probably use elimination. Right? It just makes sense. It's logical. So which equation should I alter? The first one or the second one? What do you think, Sean?
I modified the first one.
Yeah, I would agree with you, Sean. I would multiply the first one by what number?
2.
By 2.
So you'll get negative 6x plus 10y equals negative 12.
And the second, yeah?
Yeah, and then
6x minus 10y equals 12 remains the same. And then when you add them all together, nothing is left. Everything cancels out, so you get 0, which means it's infinite solutions.
Yes. So we end up getting 0 plus 0 equals 0. That is true. That is not a contradiction. So there's all real numbers, or all infinite solutions, or infinitely many solutions. Now, how could we have seen that as well? Well, just take a look at the second equation here where I'm pointing, please. This is the exact same equation as this. They're identical. Just multiply this equation by -1, you get this equation. So remember what we said. What does this look like on the graph when there's infinitely many solutions? It's going to be, let's see, first of all, the slope is negative a over b, so the slope is 3/5. The y-intercept is negative 1.2. So here's the y-intercept at negative 1.2. The slope is 3/5, so it's something positive like that. So that's the line in red. Well, the line in blue does the exact same thing. There it is. So that's what my solution to this one looks like. Infinitely many solutions occur for these two equations. Questions so far? We're doing well on time, actually. We're doing really good on time. Good? Okay, let's press on. Good job, guys. You know what? If we keep up at this pace, I think we might actually finish this lesson today. You don't have to do any video at home, which is great. All right, let's keep going. Doesn't mean not to ask questions. You should still ask questions, okay? Let's take a look at example 4, though. If 3x equals y plus 5, and 2y minus 2 equals 12k, solve for x in terms of k. Guaranteed SAT problem every year. They love these things, where you have a system of equations, but with 3 variables, so you can't get an answer. You have, you have to solve in terms of something else. Solve for one in terms of the other. So what do I do here? How do I start this? You're Sean? Somebody else got it? Nick, you answered a bunch too? How do I start a problem like this? Because I can't use elimination. I can't add straight down this variable k there. It doesn't match up.
Wouldn't you want to isolate the variables, kind of?
Okay, we can isolate variables. So give me variable x, Jim.
X.
In the first equation, right?
X is already isolated, I guess. Y.
In the first one or the second one?
Oh, wait, no. X in the first.
Okay. So if we isolate x in the first, let's take a look at what we get. All right, so right now, let's stop and talk for a second. We need to know our terminology. Remember I talked about vocab is important. Ready? This is the solution for x in terms of y. That's what this is. So we're close, right, Jimmy? We're almost there? This is the solution for x, but it's in terms of y. What do we want x to be in terms of, though, Clark?
Y. Or, I mean, we want
We want to solve for x in terms of
Y. Or K.
k. That's okay. That's all right. So it's in terms of y right now. So I don't want y. Does everybody see that? I don't want y. I want this to have a k in there. So Gus, what can I do?
So I think you would go to the second equation and isolate for y, and then you can substitute in k.
And there are other methods to do this also. There are other ways we'll discuss. But yes, I agree. Let's solve the second one for y. Add the 2 over. By the way, these are all multiples of 2. I don't know why I did that. You could divide by 2, right, in that equation also? Thinking about it now, I'm like, why did I make that happen? So y is going to equal 6k plus 1. Gus, what does that do for us? Why did you say to solve for y in the second equation, Gus? What can I do with that?
Because you have to plug it into the original thing for x. I mean, the original y for x, because it's at the solving point.
Yeah. If I plug it in there, it gets rid of y in my answer for x, and it puts k there, and that's what we want. We want x in terms of k. So this equation becomes x equals 6k plus 1 plus 5 all over 3, which is equal to 6k plus 6 all over 3, which means I divide the 3 into both, 2k plus 2. And that's my answer for this problem. I'm going to point out the fact that there are other ways to do this as well. That's not the only approach you could have taken. Clark.
Could you take out the y and then put in the 3x in the first one, and then bring that in for y in the second equation and do it that way?
Yep, absolutely. So Clark mentions another method, and that's exactly what I'm talking about. Well done. So look at the first equation, everyone. Just follow where I'm pointing. It'll help you watch what I'm doing. It's hard to follow when people talk. It's easier to see. Take a look up here. If I solve this for y instead, what does it become when you solve it for y? Sean?
Y equals 3x minus
3x
5.
minus 5 is y. Solving this right here becomes 3x minus 5. And then take this and put a 3x minus 5 in its place. And then solve this equation again for x. And that will give us x in terms of k. Questions, questions, questions. Is everybody sure that they understand this problem? This is one of those exceptions to systems of equations where you think you need, like, you're always told, if there's 2 equations, you can only have 2 variables. 3 equations, 3 variables. And for all of those systems, you can solve for a unique numerical solution. Not necessarily unique, it's different solutions, but a numerical solution. Whenever you have a third variable and only 2 equations, your answer will have a variable in it every single time. What's the most important thing about this problem is to recognize when it says solve for something in terms of something else, it's going to have that something else in the answer. So solve for x in terms of k meant that k was going to be the answer. So I know that I've got the right solution here. I've got the correct solution. Questions at all? All right, good. Awesome. Let's take a look at the last example. By the way, we're going to do this by hand right now. Part of your video watching over the weekend is that thing I talked about called a matrix. A matrix is very useful to solve a system like this. A 2-variable system, I would probably do it by hand. It's not worth the time to plug it into the calculator. You waste more time. You can do it by hand fast. But a 3-variable system, it's a messy process. But we can do it by hand, and we'll show that process. So, I've got 3 variables. I need to get it down to something I can solve easily. So my first step, God bless you, is to try to take this system and reduce it to a 2-variable system. So which variable can I choose to eliminate that works very easily? And remember, I'm not going to eliminate all of them at once. I can only choose 2 equations to add. But if I add 2 equations right now, which 2 equations can I add that will eliminate one of my variables for certainty? Which 2 equations can I add that will guarantee eliminate one of them? Yeah, Sean, Sam, very good, Sam. Add equations 2 and 3 together. I would agree with Sam. Does everybody else see that? Yeah. You could do something else, but then you'd have to change the equations. So I'm going to start with my first command and say equation 2 plus equation 3. And because I'm not altering them, I'm not going to rewrite them again like I did last time. It's just a waste of time. Because I'm not altering them. The minute I start to alter my equations, I should rewrite them below the command prompt here. But I know that I don't have to, so I'm literally going to add straight down. What happens to x? Crosses off. What does y become? 6y when I add those 2 together. How about z? Negative 10z. And my constants? 4. Now, we have a new equation. What should I call it? It's brand new. It's not an altered form. Oh, I'm like, what's going on? We'll do example, I promise. What am I going to call this equation? What am I going to call this equation? We'll do example.
Equation 4.
Yes, let's call it equation 4. Good job. It's a new equation. So what do I need now? If I really want to solve this problem, I've got a new equation with only y and z. Can I solve it right now?
No.
What do I need? What do I need to solve an equation that's 2 variables?
Get rid of one.
I need to get rid of one of them. But I can't do that because I only have 1 equation. So what do I need? What do I need? Another equation with only what variables?
Y.
Y and z. I need a 5th, equation number 5, with only y and z. So I already operated on equations 2 and 3. Does everybody see that? So I can't use equations 2 and 3 again together. But now I can use equations 1 and 3 or equations 1 and 2 and combine them in some way to get rid of x again. To get rid of x again. So equations 1 and 2 or equations 1 and 3. It doesn't matter. It's 6 1/2 dozen. It doesn't really matter. Which one do you suggest? Give me a suggestion, Sean. Go ahead. 1 and 2 I would agree with. I would multiply equation 2 by 2. Literally multiply this whole thing by 2. So again, I'm going to take equation number 1. And to that I'm going to add 2 times equation number 2. Now, because I'm altering it, I'm going to rewrite them. If you get good enough at this, you don't have to write them God bless you, every time. But I'm going to rewrite them just because I'm altering it. And I don't want to make any mistakes. A lot of room for error in this process. A lot of room for error. Add straight down. Make sure my work is right, please. Somebody check me. And I'm calling that equation 5.
Yeah.
Good? I'm going to call it at this point because I do want to do examine it. I think examine is actually very important. So I'm going to call it. But can we agree that it's easy to solve now? Because now what do you have? 2 variables and how many equations? 2 equations. So for your homework over the weekend, obviously, finish by solving equations 4 and 5 as a system. That will yield your answers for y and z. What do I also need to figure out? X. So your answer will be a triple coordinate. X, comma, y, comma, z. So finish up solving 4 and 5 this weekend. That'll give you that will give you y equals and z equals. From those two, plug both of those in at the same time, and I would choose equation 3 to plug them into, because then you could easily solve for x, which has a unity coefficient. And again, my answer is going to be x, comma, y, comma, z. Gus?
So the videos at the bottom of what we're going to do to watch or...
So the homework, let me pause and go on the line. So this is the homework right here. The normal homework is this. These are your extra resources if you want, Gus. This is not the videos I'm talking about. The videos that I'm talking about are on Moodle under videos from class and video resources, or additional resources I call it. You'll see there are 2 videos. One says matrix, one says intersection method on the calculator. Just things we wouldn't have time for, okay? And next class I want to get into 3.6 still because it relates to 3.5. So I'm not going to use that time in class. So over the weekend, 2 videos to watch and your homework to finish.